Hello, welcome back to the part 5 of this series video on the topic series. In my part 1, I discussed summation by parts. In my part 2 of this video series, I discussed absolute convergence. In my part 3, I discussed about the algebra of series, and I put emphasis on the Cauchy products. In my part 4, I discuss rearrangements of series. In this part 5, I'm going to be talking about some of the examples. So this video is dedicated to examples. So I'm going to go down now to, these are the previous discussion I had in my previous videos. So I'm going down to where I stopped on slide 20. This video is extremely important, especially to say how we can examine whether a series converges absolutely or just convergent or conditionally, which means it converges but does not converge absolutely. So if a series converges but does not converge absolutely, we say it converges conditionally, or it doesn't even converge at all. So I'm going to be looking at 5 different examples in this case, and this list is not exhaustive. There are so many questions in my worksheets, and that students can lay hand on and practice more problems. All right, so let's start with example 1. What you do generally is to take the sequence inside the sum. So in this case, we call the sequence an, which is -1 to n into n plus 1 over 2 times 1 over 3 to the n. When you want to show that a series converges absolutely, you need to take the absolute value of the sequence of the series. So when I take absolute value of this, the absolute value of the first term here is just 1, because this term is either -1 or +1, depending on what n is. So when I take absolute value of that, it disappears. So what I will only have is 1 over 3 to the n. Now, so the series now of absolute value of an is simply the series of 1 over 3 to the n. I can pull everything together in parentheses. So I'm going to have the sum of 1 over 3 to the power n. Obviously, this is a geometric series, and where the ratio is 1 over 3. We've shown in the previous discussion that when the ratio is less than 1, then the series converges. So this series converges absolutely, because we've just shown that when we put absolute value of an, what we get, the series of that converges. And if a series converges absolutely, then it converges as well. So that's the first example. The second example is given by the series sum of n equals to 1 to infinity of cosine n over n squared. If I take n to be the sequence inside the series, and I take absolute value, clearly absolute value of cosine n oscillates between -1 and 1, so absolute value of that is just 1. So the entire term here is less or equal to 1 over n squared. And so we know that if I take the sum of 1 over n squared, that series converges because of the p series. So p is 2 here, which is bigger than 1. So by comparison test, this series, the series of the absolute value of an, which is less or equal to the series of 1 over n squared, if the series in the left in the right converges, that the series behind it on the left converges as well. And so since the series observable value of AN converges, we then say that the original series converges absolutely. And in this case, again, because it converges absolutely, then it converges as well. All right, here is another example. I want you to take a second to look into it and see if we can get the answer for this. So AN is given by this. We take the absolute value of AN, and so this alternating part will disappear because of the absolute value. So all you get left is 1 over n cube. And exactly what we did before. If I take the series now, I'm going to have this side here converges because 1 over n cube is a sum of 1 over n cube is a p series. P is 3 bigger than 1. So by p series, this converges, so which means this converges, and that gives us that the original series converges absolutely. We are so lucky that some of these examples actually converges absolutely. Number 4, we have the sum from n equals to 2 to infinity of -1 to n over n squared plus 1. In this case, an is also given by -1 to the n over n squared plus 1. If I take absolute value on both sides, I'm going to have absolute value of the numerator is just 1, so 1 over n squared plus 1. We know from our previous discussion that 1 over n squared plus 1 is less than or equal to 1 over n squared. So this is more or less like example in the second example. So the series given by the right-hand side, if it converges, then the series given by this left-hand side also converges. And we know that the series given by this one is P series, which converges. Therefore, this one also converges. Then we can conclude that the original series given to us converges absolutely. Now let's see question 5. Maybe we can get something different from here. Again, this question 5 is the sum from n equals to 1 to infinity of -3 to the n over n squared. So in that example, an is given by -3 to the n over n squared. When I take absolute value, what it means is that the negative sign here, if I separate this numerator to be -1 to the n times 3 to the n, the -1 to the n will disappear. We become 1, and so I'm going to have 3 to the n over n squared. Now, it looks like ratio test will be best in this case, so I'm taking the ratio an plus 1 over an, which is the n plus 1 is 3 to the n plus 1 over n plus 1 square times the an. Now I invert the fraction because I want it to be multiplication. So it's n squared over 3 to the n. You do the algebra, you get 3 times n squared over n plus 1 squared. All right, so we are going to get, when by the time I take the limit of this guy, the lim sup, and the limit in this case is the same since the limit exists. So if I take the limit of this guy, because I have n squared here and I have n plus 1 squared here, so the limit of this is just 3, which is bigger than 1. By ratio test, when this limit is bigger than 1, then the series given by an diverges. And so this series does not converge absolutely. If it diverges in the first place, it does not converge absolutely. So this is a good example of a series that does not converge absolutely. Furthermore, because we have seen that the series may not converge absolutely but converges. But in this case, this series an here the limit of this an does not exist, so it does not go to zero. We have shown that if the series of an converges, then an has to go to zero. That's the condition that we have discussed before. But here, if the series of this an converges, then the limit as n goes to infinity of an has to be zero. But we know that this is alternative series, so it goes from -3, it's alternating, the sign is alternating, so the series does not exist, the limit does not exist, and so we can make conclusion that the original series also diverges. So it's not absolutely convergent, and it's not even convergent at all. And so this is the end of this series of videos. It's part 1, part 2, part 3, and part 4, and part 5. And I hope you enjoy watching it. I break it down into smaller pieces so that it's easier to watch. And I hope you enjoy it. And my advice will be, as you watch this video, take note, write your own notes, and expand more on it. And thank you for taking your time to watch the video. Bye.